Very big thank you to the organizers for letting me speak here. It's a great honor to be here, and I've really enjoyed my stay so far. Yes, so before I forget to say it, all of this is joint work with Christian Carrick and Jack Davies, and let me also say it once that today this is a p=2 talk. The other primes, as far as TMF is concerned, are so easy that they're not worth talking about if you look at the p=2 case. Okay, so let me just start with the goal of what I want to talk about. My goal will be to resolve a circularity in the literature regarding the homotopy groups of TMF. Now, of course, aside from the fact that as mathematicians we don't like circular reasonings, one reason why you might care about TMF in particular is because this tells us a lot about the sphere spectrum. So, okay, you could say this thing is a ring, so it has a unit map from the sphere spectrum, and this map detects a lot of elements in the sphere, like has a very non-trivial array-witch image. But at the same time, this is much easier, in some sense, almost like in the connective sense, it's periodic. So this allows you to construct periodic families in the sphere because this is much easier in high degrees than this thing is. Okay, and of course there's the big thing in this talk is going to be I'm going to use synthetic spectra to compute this thing. And I actually very much agree with Oscar's rant. Like, lots of this is just filtered things, but there will be one key thing which is truly synthetic and not just filtered. But I'm also very happy to talk about the difference afterwards, in case you're curious. Okay, yeah, so I want to start off with some background, or why am I making this claim that there is some circularity to begin with. And the circularity arises in sort of the how of how this map is helping you understand the sphere. Namely, this is about the Adams-Novikov spectral sequence for TMF. So of course, how do you start a computation like this? Well, first you have a look at the E2 page. And how do you usually compute the E2 page? Well, you're going to look at the homology. So in this case, the MU homology TMF. Okay, and Tilman Bauer very in lots of detail tells you how to go from this homology to the E2 page, but this sort of raises the question how you arrive at this homology. And this is more difficult because, okay, I don't really want to get into constructions today, but sort of as a reminder, this thing I've been denoting by lowercase TMF, it's defined as the connective cover of some other variant, which unfortunately the only way to distinguish it is by a different capitalization. But this upper T, lower MF, this is something which really comes about as something in spectral algebraic geometry. So this is the global sections of some sheaf of spectra on some stack, whereas this is in some sense more an ad hoc construction. So because of this algebraic geometry, so if I have a good handle on computing things like the homology of this thing. So this is all good, and passing from this to the other is not so clear, like just from that definition you're not going to do it. But there is a thing you can do. Namely, if you know a bit about the homotopy of this middle upper T, lower MF thing, that is sort of information that feeds into this implication. This is what the Q-Matthew shows. And the particular fact you need is that this has a gap in it. So the first 20 negative homotopy groups vanish. This is something that turns out to be of importance. Okay, so how do you compute these homotopy groups? That's sort of where the namesake object comes in. You have a certain descent spectral sequence, which I'll tell you more about in a bit, but again, comes about by its algebrogeometric definition. Okay, and then you think, where is the computation of this written down? And this uses as input the Adams-Novikov spectral sequence for TMF. Okay, and this, well, I have a rather unfortunate circle going on there. And the fix that I want to propose to you today is to sort of do this, but without depending on this input over here. So, and what I will label this thing as is I'm going to compute the bi-graded homotopy groups of something I label synthetic modular forms, which implies this, sort of once you go around the circle, you get the E2 page, it sort of replaces this arrow. So in that sense, it also implies the Adams-Novikov spectral sequence for connective TMF. Okay. Yes, and in particular, like the main result of this computation is indeed this gap theorem that I talked about. So the homotopy groups of TMF vanish in the range between -21 and 0. Okay, and this is, okay, it's a specific computation, but I really believe that the computational methods are much more general. Like most of them apply to any spectral sequence if you look at it in the right way. So this is really just an example computation that is like elegant to see, but you don't need to be interested in TMF specifically to be interested in these techniques. Okay, I want to talk a bit more about what the computation roughly looks like and why okay, nobody set out to make a circle like this, or why this whole story is so difficult. Yes, and this is the second thing, so more about the descent spectral sequence. So I am on the other end of this shearing for grading, so I'm going to use Adams grading throughout. So this descent spectral sequence is going to be of the shape, you go from sheaf cohomology, and the particular variant of elliptic curves that I'm using is the compactified stack of elliptic curves. Okay, it doesn't really matter all too much, but it's a spectral sequence which arises from the definition of this thing as a global sections of a sheaf of spectra, and it starts with the cohomology of this stack, and you arrive at the homotopy groups of this spectrum. Yeah, it's like the usual thing on the modular formal group, so this two periodic. Because the sheaf of ring spectra is like a two periodic sheaf, so it's like locally Landbarber exact in a two periodic way. Okay, well, I'm not going to draw the whole picture in complete detail. That would be impossible to do by hand, but I want to give you a sketch of what the rough shape looks like. So sort of in Adams grading, so in n, s coordinates. What does this look like? Well, there's a particular line of slope 1/5. It's not quite a vanishing line, but below this line, you sort of after the fact, you find that here you have the Adams-Novikov of connective TMF sitting in there, sort of in the connective half. And then above this line and in the negative stem, so I shouldn't have drawn this far, this is what I'm going to call the non-connective region. Which might sound a bit silly because it goes into the positive stems, but the point is that all of the stuff that is in positive stems but in high filtration, it's going to die out from the differentials. That's sort of what turns out to be, so this doesn't really contribute. And in another sense, it sort of comes from multiplying an element in negative stems with some high filtration element to move it to the right. Okay. Now, so the difference between the Adams-Novikov for little TMF and this thing is that you just have a lot more junk to the left and in high filtration. So you need to do sort of three things. You need to, on the one hand, establish what I'll call connective differentials. Which is like things like this, which don't cross this line. Secondly, establish non-connective differentials. Which are things that live completely above this line. And then lastly, you need to exclude line crossing differentials. Because this would exactly say that the final answer is going to be different than if you had sort of just looked at this thing in isolation, because it would mean that these two parts are going to somehow mess with each other. So the thing that you don't want to see happening is this number 3 over there. Okay. And perhaps you were wondering why in a story about Adams-Novikov spectral sequences, I suddenly started talking about this here thing. You could have looked at the Adams-Novikov for this TMF instead, but it turns out that you don't really want to. So numbers 2 and 3, sorry, maybe I should flip the boards. Maybe not. Okay, numbers 2 and 3 make the descent spectral sequence preferable over Adams-Novikov for non-connective TMF. And the reason is, it sounds very innocent at first. The end computation is going to, the E2 patch is going to look the same, except that the Adams-Novikov moves the non-connective region down by 1 filtration, just vertically downwards. And this ends up meaning that 2 and 3 are just impossible to do. At least I see no way of how to do it internally to that spectral sequence. Because the reason is, sort of once you grant number 1, you can, by just spectral sequence arguments, deduce numbers 2 and 3. And the way you do this is there is a certain class, which is called delta to the 8th, which is a permanent cycle. And this is somehow acts as a sort of periodicity element. So any element in the non-connective region in the descent spectral sequence, you can multiply by delta to the 8th, and it will never be 0 if it wasn't 0 to begin with. So there's no delta to the 8th torsion. And that means that by the Leibniz rule, you can deduce differentials over there by differentials under this line. Whereas just in the Adams-Novikov spectral sequence, just for degree reasons, if you shift everything down, there's no longer any room for this to be non-delta torsion. So all of this is delta torsion, and it's, yeah, there's just no, so that sort of excludes number 2. And then number 3 also becomes more difficult because it turns out that often in the descent, things are just about right. Like there's a potential D11, say, but the target ends up supporting a D11 itself. That means that the D11 at the bottom couldn't have existed. Whereas like in the Adams-Novikov, it would look like a potential D10 to something that supports a D11, which doesn't quite work like that. So this is sort of why you want to work with the descent. There's a big problem. There's no evident map from the Adams-Novikov for the sphere to descent for TMF. And why is this so important? It's exactly because you have all of this junk in high filtration. Because usually, like, you kickstart a computation by saying, okay, I have some classes like eta and nu, or maybe some higher classes which are permanent for degree reasons. That's what happens in the sphere. And you use these to kickstart and build off of later things. But over here, like, for degree reasons, there could be differentials on all of these things, which you have to somehow rule out. And if you had such a map, you could do this, but you don't have such a map. And then, okay, that's a smaller point, but then even if you could exclude these differentials, you also have to deal with the fact that everything is only defined up to higher filtration, and things become a lot more annoying in that way. And if you could import low-dimensional info from the sphere, this would be very convenient, but you don't have this. Yes, and then finally, there are a few key differentials which are missing in the literature, or at least if you look at proofs that are available, they sort of rely on this circle that I drew below there. So I don't think there's sort of in the literature, there's no recorded proof of these few key differentials. Okay, and then the solution to all of these problems is, let's say, to implement this spectral sequence as a synthetic spectrum. And that's where I want to get to next. Any questions so far? So my slogan for synthetic spectra is the following. I would say that the relationship that synthetic spectra have to Adams spectral sequences is in many ways similar to the relation that spectra themselves have to homology theories. Okay, and maybe to be precise, there's always some flavor of Adams spectral sequence, so I should join both of these with an E. Okay, and one concrete thing that I mean by this, for instance, is that synthetic spectra, they form an infinity category, but a rather nice one, so it's a presentably symmetric monoidal one, even a stable one. You can probably say more things, like it's compactly generated by dualizable objects, the unit is compact, things like this. Okay, that sort of makes it a homotopy theory. And then we have two lax symmetric monoidal functors. One going from spectra into synthetic spectra, denoted by nu, not to be confused by the stable homotopy element. And the other, sort of fitting with the theme of using lowercase Greek letters, we started calling it sigma, which goes from synthetic spectra to filtered spectra. So diagrams from the PO set Z into spectra. So we have transition maps. The first of these, called the synthetic analog, and the other one we started calling it the signature. Okay, and I heard that Jack has sort of been preparing the way for me in talking about the signature, but let me nevertheless recall some of the key facts of this thing. So really, sigma, I like to think about as somehow an underlying spectral sequence functor. Like if you regard the infinity category of filtered spectra as like the homotopy theory of all spectral sequences, this is exactly forgetting whatever additional structure synthetic spectra have over a general spectral sequence. Like one theorem, which you can formulate in different ways, but you'll find it in the works of Piotr Pstrągowski, of course, also in a collaboration he did with Pachkoria, also in the works of Birkeland, Hans Sanger. Is that the composite of sigma after nu, I'll just say, is the E-based Adams spectral sequence as a functor from spectra to filtered spectra. You can make very precise what this means, but I don't want to get into too many of technical details right now. Okay, but so far I haven't sort of said what the point is of having this category that lives over filtered spectra. And the thing is that this is geared specifically to Adams spectral sequences. So one example of this phenomena is you can look at the unit for this monoidal structure, which turns out to be the synthetic analog of the sphere spectrum. Okay, and just by being the unit in a monoidal category, this is going to be canonically an E-infinity algebra, but it's not just any old E-infinity algebra, it's also the initial one. Whereas if you just think about filtered spectra, like the Adams filtration on the sphere has no universal property in filtered spectra. Okay, and then the main thing for why I want to talk about synthetic spectra in the first place is this construction / theorem that I did with Christian and Jack, is that we constructed what we called synthetic modular forms. We constructed this as an E-infinity ring in mu synthetic spectra. So this is an Adams-Novikov story, as you might expect. But we also provide an equivalence of the signature with the descent spectral sequence for TMF. Okay, you can sort of think about this in a very multiplicatively coherent way as well. But if you like, you can also just think about this as underlying spectral sequences. Okay. And this is, in fact, this key step where I said that you need synthetic over filtered spectra, because by virtue of living in this category where the unit has is the initial object, you, for free, get a map from the synthetic analog of the sphere into SMF, which, once you hit it with sigma, is giving you exactly this map that I said before was so hard to obtain. I think it's even on the board behind me. Yes. So this map is just now given to you for free by this construction. Okay, but we got more than we asked for, and this is a very good thing, because there I just asked for a map of spectral sequences, but here I get an E infinity map. And you could even forget down to an E infinity map there, because this thing is lax monoidal. And the fact that this is an E infinity map also allows you to import Toto brackets and whatnot. And that in the computation turns out to be very important in addition to just importing a set number of elements. You also need some Toto bracket expressions for these. Okay. Maybe one remark for those of you who are motivically minded. This SMF gadget is what is called an even synthetic spectrum. And there's this equivalence between even mu synthetic spectra and C-motivic spectra, at least up to P completion. So what you learn is that after P completion, this thing is an object of at least a cellular stable homotopy category over spec C. And the other thing is that no. Yeah, it's a limit of mu modules, but it's not an mu module itself. Yeah, and then sort of this synthetic analog of TMF, which encodes the Adams-Novikov spectral sequence, is not even. So it does not define an element in the motivic category. Okay, even without like making reference to the motivic category, this is sort of explaining why this descent spectral sequence is so preferable over the Adams-Novikov. Because this even business is just saying that it's concentrated in even total degrees. So it's like the differentials have this checkerboard pattern. You only have odd length differentials. Because I shifted stuff down by one filtration, this is not true over there. So this is a very structured way of making this difference very precise. Okay, and yes, but that is just the synthetic analog of lower TMF. So it's so this is a very different in that sense. So we don't just take the synthetic analog. But I would also like hesitate to call this motivic modular forms, because it's really, I just get a cellular thing because it's by nature really a synthetic thing. Sorry?
You say again what even means?
You can define it as generated, so the even category is the localizing subcategory generated by the even spheres, which is exactly those like concentrated in even total degree. And because this spectral sequence is convergent, it sort of boils down to checking that the E2 page is even. Okay. So far I've just been talking about very structural properties of synthetic spectra, but now I wanted to get into the computational reasons. And this is also something that could have been phrased purely in filtered spectra and could have been done very long ago. Like, this is somehow not very modern, but in synthetic spectra it just looks very new. Okay, so I'm just going to flash a definition of a certain bigraded sphere in synthetic spectra at you. The precise formulation doesn't really matter. I can now just say that I've given you the definition. So for two integers n and s, I define the n, s sphere as the minus s-fold suspension of the analog of the n plus s sphere, and the point is that nu does not preserve suspensions. So this is not a stupid thing to do. And then, as you might expect, the homotopy groups are just going to be homotopy classes out of this thing. Okay, and then the reason why I index this thing is because I'm using Adams indexing. So the slogan is going to be that if you have a synthetic spectrum, then pi n comma s of this thing, it captures information about stem n and filtration S and higher. So not just about that filtration S, but also all of the things above it. Okay, and making this precise is going to be a bit of a mouthful, but I give you like a slightly reduced version of this mouthful. So first we're going to talk about this magic map, which is tau, which in this grading that I'm using is living in the 0, -1 degree of the sphere. The definition isn't very interesting. It's just like if you unravel what this definition is, it's going to be the suspension comparison map, essentially. Almost even. Okay. And one computational fact that I will use is if you take a synthetic spectrum and you cone off tau on this thing. So I sort of regard tau as an endomorphism of x by tensoring x with this map. And then I take the cofiber. And for every n and s, there is a canonical isomorphism between that and the E2 page of this spectral sequence, which I've labeled sigma of x. And just to say one word about indexing conventions, I've by choice made the spectral sequence look like it starts on the E2 page. That's just to make it fit nicely with how you usually index Adams spectral sequences on the E2 page. Okay. And then the big theorem, which you'll find in the work of Birkeland, Hahn, and Sanger, you'll find it there in the case where x is a synthetic analog, but you can generalize it to any synthetic spectrum using this signature thing that I talked about. Okay, so you fix a synthetic spectrum. I'm going to give you two parts of this thing. So if I have a class little x on the E2 page, so by this proposition, I can regard this as an element in the cofiber of tau on x. I can ask whether it lifts back to the integral element of x. So this lifts to pi n comma s of x without this cofiber. This happens if and only if x is a permanent cycle. Okay, and if this happens, then there exists a particularly good choice of lift alpha, which will satisfy the following, namely tau to the r times alpha is 0, so it's tau to the r torsion if and only if there is some differential of length at most r plus 1 that hits x. So really, if you choose your r minimal to make this alpha tau to the r torsion, then it's going to be exactly a dr plus 1 differential. And the plus 1 is because I started things on the E2 page instead of the E1 page. Okay, and I'm sort of granting myself convergence conditions, but granting this, in some sense, all elements arise this way. Meaning that you regard this as a z tau module, and you produce elements by lifting them if they're permanent, and then you also adjoin other tau multiples. Some of them will be 0 exactly when you have differentials. Okay. Maybe as one sanity check before I move on to point 2 is corollary of this, that if you take the bigraded homotopy of the synthetic analog of a regular old spectrum, and if you invert this tau, well, then you're exactly killing all the things which are tau power torsion, which by 1 is exactly the differentials. So this is going to be just the homotopy groups of Y, or at least like you adjoin some polynomial generator. Just a bit funny looking. Okay. So for part 2, I will fix some integer k at least 1, sorry. I'm going to do the same thing for x mod tau to the k instead of the integral k. So I have a similar thing. I start with the 2 elements, and this thing lifts to the homotopy of x mod tau to the k, this time if and only if x is a d less than or equal to k plus 1 cycle. So you only need to survive or not support finitely many differentials. And again, if this happens, then there exists some lift alpha with the property that, well, the same sort of thing, except that you have a bound on R. So this conclusion is only valid for R less than k, and somehow the point of this thing is that, in addition, tau to the k is 0 on this thing. Okay, you need.
Is x the less equal to k cycle or less equal to k plus 1 cycle? K is 1.
Oh, k, yes, sorry. Thank you. Okay, and here you need to be slightly more careful about saying that this is everything. I will gloss over this for now. But the point for me is that this last thing is true, which, as we will see, somehow allows you to ignore elements of very high filtration, at least if you work in this truncated object instead. All right, any questions so far? Okay, then I'd like to get into some of the computational facts. And sort of as I said in the beginning, okay, I'll just draw the picture again for you. So the spectral sequence that we're looking at sort of divided into 2 regions, and I said that by spectral sequence arguments not involving anything fancy, if you can prove all the differentials happening there, you can deduce all of these other differentials. So the key is actually to focus on this thing, and I'm not going to talk about the non-connective region much anymore. So I want to really talk about 2 differentials which were like unknown or only sketched before. But to do this, I want to give you one warm-up differential, which is going to introduce you to some of the concepts that you use in the synthetic or filtered setting. Okay, so first thing, this is just a formula or claim that I want to start my computation with, is that there is a particular differential which hits h2 times g. So to make a translation table, I'm going to use some names h1, h2, and g. And these are going to be my E2 names for the element eta, nu, and kappa bar. And the sort of stem filtration is going to be 1, 1, 4, 1, and sorry? Oh, yes. Thank you. Oh boy. Okay. Yes, so I have this differential over here. which I'll just say briefly, this follows from the sphere. Like, it's not quite that you have this exact differential in the sphere, because delta isn't an element in the sphere, but like h2 cubed times g is hit in the sphere, and then that thing also has to be hit in this descent spectral sequence because I have this map, and then this thing is just the one that has to happen by the Leibniz rule. Okay, and the claim that I want to prove to you is that it follows from this that you have a d7 on 4 delta hitting h1 cubed times g. Okay, and the idea behind this is that you have a hidden extension of the form 4 times nu is eta cubed. And maybe if you're thinking F2 atoms, this doesn't look very hidden to you, but in the Adams-Novikov, this is in fact a hidden extension because the integers have filtration 0. So in a picture, if you draw eta like this, you have eta cubed up there, and nu, or H2, sits in a group which is a Z mod 4, and then sort of this outer circle, which is the 2 multiples, is connected to this eta cubed. Because the integers in Adams-Novikov have filtration 0. So this is filtration 0 and 1, and this is filtration 3, and that makes it, yeah, in other words, the product 4 times H2 is 0 on the E2 page. Now, I'm going to be very naive for a second, because an argument you might want to try and make is to just plug in the linearity of the differential. And if you were like extremely sloppy in sort of equating both sides of this table, then you might say that, okay, the differential on delta is going to be 4 nu times kappa bar, but 4 nu is eta cubed kappa bar, and this would sort of give me the differential, except that this is of course complete nonsense because I should really be working with E2 elements, and this product is just on the E2 page is just not equal. Like, this product here is 0. And of course, like, the claim also never talked about a D5, but it talked about a D7. Yet still there is a way to use this hidden extension to deduce a D7, and that uses something we call the total differential. So what is this thing? I'll just talk about it in the case for this SMF object. So if you have 2 integers, little n and big N, and there is a map which are called partial lower n, upper big N, and the degrees are, it goes from mod tau to the little n into some shift of mod the power of the difference. Okay, the definition is just, it's the boundary map for multiplication by tau to the little n. How it arises doesn't, the point is that this thing captures the differentials little dn plus 1, dn plus 2, all the way up to d big N. So what do I mean by captures? Well, for instance, one thing I mean is that little partial n, upper n plus 1, this is the differential dn plus 1, or at least like an E2 page representative of this map. And in general, how this thing captures the higher differentials is you can ask the question of whether the value of this thing becomes tau divisible in there. Like, maybe it's not. If it's not tau divisible, then the mod tau reduction, and the mod tau is the E2 page, then the mod tau reduction is the value of this differential. Okay, now if it is tau divisible, then you can divide it by tau, and the mod tau reduction of that thing is going to be the dn+2 differential. And you can keep going like this until you hit there. And sort of because I've truncated this up to big N, you're not going to see any of the higher differentials, because this thing is always going to be n minus n, tau to that divisible. Okay, and now the differential that I had over there, let me give it a name. So this thing star, it upgrades to the statement that delta for 8 on delta is equal to nu times kappa bar. So let me unpack this statement for a bit. So delta for 8, it's going to start in SMF mod tau to the 4th. So I need to first argue that this thing is an element in there. And for that, I look at the theorem on the back. So delta is an E2 page element. And to lift it to x mod tau to the 4th, I need to argue that it's a d less than or equal to 4th cycle. And that's just something that you check. I mean, I sort of implicitly told you this by saying there's a d5 differential. And it turns out it lifts uniquely, but I don't want to get into the combinatorics of that. Okay, and then these elements, like they are elements in SMF without any mod tau reductions. So I implicitly reduce this mod tau to the 4th to make it an element in there. Okay, so strictly speaking, there is more information in this than purely in this claim. Like you cannot deduce it strictly speaking, but sort of setting things up correctly do allow you to do this. And by setting up correctly, I mean exactly that I put an 8 in there. Because this is this other fact about truncations is that you have this tau to the, in this case, 4th is 0 on my object. So I'm ignoring all all filtrations that are more than 4 above me. So if I like have my class delta over here, and I have some d5 differential hitting this box, I'm only going to see 4 differentials above this, and I'm ignoring all the higher things. So this sort of gets me around this problem that I have an enormous amount of junk in high filtration, and I always need to think about, is this actually the correct element or only up to higher filtration things? This just lets me do it without having to think about it much. Okay, sort of once you have this set up, this very naive thing just works like a charm. Because this thing is this thing is linear over the integers. The fact of being in a stable category. So I can pull the 4 out, and then I have this here. But this is an equation that, let me remind you, is living in SMF mod tau to the 4th. And then
We're checking an identity in a Z1 to 8 by its reduction 1, 2, so that it could be a factor 5 there.
Yes, so like this is the thing you actually show to show that instead. So it's not really that I'm not sort of really going from there to there, but okay, sorry. Okay, and the key fact of this hidden extension, synthetically, or even this is just a filtered fact, filtered abelian groups even. This hidden extension translates to this statement that 4 nu is equal to tau squared times eta cubed. Now, if you remember that tau has by degree 0 minus 1, that's sort of, in some sense, this is inserted to make the degrees work out, because this has filtration 1 and this has filtration 3, so I have to subtract 2 to make it work. But also, if you just think about what a filtered abelian group is, and you interpret this tau as the shift down infiltration map, this is exactly what it means to have this hidden extension in this filtered abelian group. Okay, so with this knowledge of the hidden extension, I know that this product is going to be tau squared times eta cubed kappa bar. And okay, so I've now shown that this total differential is more tau divisible than the one I started with. So the one that I started with was encoding a D5, but it's twice as tau divisible, so it encodes a D7. So from this captures quote, I learned that I have this differential. Right. Well, I sort of presented this deduction as something that you use synthetic or filtered spectra for to do. This is something that you could have done without all of this technology. But the following is something where you couldn't really have done this, because at least to my knowledge, there was no recorded proof, or at least not relying on this whole circularity business of this this differential. And in fact, this differential is the key thing that a lot of other differentials rest on. This is the differential that looks like this. So it's again a D7, but this time it's not on 4 delta, but delta to the 4th. And again, you run into the problem that the Leibniz rule just doesn't give you any information, because delta is supports a D5. So delta is not an element on the E7 page, so you can't use like a Leibniz rule to deduce anything about this 4th power. Like this thing is indecomposable on the E7 page. So the thing that's going to help you is that this total differential has a much better Leibniz rule. And this is a theorem of Birkeland, which says that delta lower n upper 2n is a derivation. Now, why do I call this an improved Leibniz rule? Sort of, if you work out the thing I meant by captures, then the total differential lower n upper n plus 1, the fact that this is a derivation gives the ordinary Leibniz rule. So the point is that this thing is able to capture a lot more differentials, and the amount that you can capture in addition to the ordinary one is sort of dependent on which page you're working at. Like the bigger this n is, the more power you're going to get out of this result. And the thing I just did is I worked with this delta on SMF mod tau to the 4th. So I can apply this to my total differential I had earlier, so proof of the proposition. I just use this Leibniz rule, so delta for 8 of delta to the 4th is for delta cubed times the differential. Okay. Okay, I've just shuffled the things, but again, I see the same 4 new appearing, which is going to give me a tau squared for the same reason as before, like this. And now if I apply this claim of I divide this by tau twice and then reduce mod tau, so I'm just reducing this part here mod tau, then I learn the differential that I wanted. Okay, maybe a quick sanity check, because this is a little bit of a funny phenomenon. Usually you can't work with delta as an element in the homotopy groups because it supports differentials. But in this case, I'm working in the target in SMF mod tau to the 4th, and delta is an element there. So this here truly is a 3rd power, which is something Like if I had increased this 8 any higher, then I couldn't have made this argument. All right. Now for one final differential, which is the sort of last one in this entire computation. So this was one of the first hurdles you're going to hit if you're running this computation. And afterwards, like the same techniques of using total differentials are going to give you all of the other things. It's just some beefed up version of the Leibniz rule, if you will. The following is required a very different argument, and it's a differential of a much greater length. It's a D23 differential. And it's hitting g to the 6th. So this is in essence saying that kappa bar to the 6th maps to 0 in TMF. Like by Nishida nilpotence, this thing has to be nilpotent, and in TMF the nilpotent exponent happens to be 6. Okay. So we're instead going to show something different. Because this omnibus theorem, it said that differentials translate to tau torsion, or tau power torsion. So instead, what I will do is I'll show that the equation tau to the 22 times kappa bar to the 6th is 0. And okay, if I just want to know that this differential happens, I can check this modulo any power of tau that's great enough to see this 22nd, so I can pick the 24th, or could have picked the 23rd, but these two things happen to be more or less the same, because by this evenness property. Okay. And we use a certain Toda bracket expression, and this Toda bracket, it comes from the sphere. So kappa bar sits in the Toda bracket kappa to eta num. Okay, I have to put a factor of tau squared there, which is accounting for the fact that in the sphere, in Adams-Novikov, kappa bar has filtration 2, TMF just happens to have filtration 4. So sort of if I import this, this is what that ends up translating to. Okay, and now I can just use some juggling magic. To start with the equation I want to prove something about, I'll just pull some kappa bars and taus to either side of this bracket. Like so. And okay, I can apply a shuffling formula. And this drops out. And the reason I chose these numbers to, or these factors to be like this, is so that I would get this nu times tau to the 4th kappa bar at the end, which should still be up there, is exactly this element. So this D5 differential that was hitting this element, it's exactly going to translate into the fact that this number is 0. So, okay. Number is in bracket times 0. So this number is 0, and therefore the equation holds, and that shows the differential.
So this only shows that D26 is hit by a differential, but then there's no other possibility?
Exactly. Yeah, it's just for degree reasons, there are no up to D22 differentials, and this has to be the only one for degree reasons. But the key point is that there has to be the D23 that does it. So this is the only hard part about this. Okay.
Roll with the 22 here, but the tau to the 16 seems to do nothing.
So the subtlety is that I have to justify why I can apply the shuffling formula. And because I'm working with a four-fold bracket, you should really be careful. And the point is that to do this, you have to check that all the three-fold sub-brackets of both of these things are strictly 0. And that's why I had to put the tau 16 there, because there is a differential hitting something. And this is also the reason why I'm running this in a truncation of SMF and why I couldn't do this integrally or even just non-synthetically, because you might think like, look at this and remove all the taus from the board, and that should be an ordinary argument in the ordinary TMF. But the point is you have to justify why this shuffling formula works. And that again brings you into the point of you only know things up to higher filtration, and at this point you don't know all the D23s yet. So you have to somehow ignore these things, and this does all of that for you. So that's why it's sort of hidden in the way I wrote this, but you have to do these very careful checks, and that's why you choose these numbers to look like this. Okay. So these are the sort of techniques that I wanted to highlight for you. And let me just end by saying that in addition, if you have all of these total differentials that you compute by methods like this, you can use those total differentials to then also learn the hidden extensions. So for instance, you can solve all of the hidden 2 extensions just from all of the total differentials that you run. It's another upgrade that this synthetic perspective gives you. Yeah. And in the end, this is how you compute the descent spectral sequence for TMF. So, thank you for your attention.
Thank you for very
Questions? Can you remind me, is the construction of SMF, you apply synthetic analog to the structure sheet with NL bar and then take the limit?
Yes, exactly.
the brackets you're using, do you ever use commutativity?
I don't think we do, no.
In the Adams spectral sequence, there is sort of a power operation argument with the fourth as a
Right.
square.
Yeah, there's something that I was wondering if this synthetic Leibniz rule over there is somehow connected to this. I don't have a good way of saying that, but it certainly looks similar in spirit.
Yeah, I mean, the Buscoria paper probably says something about product structures.
Yeah.
I don't think it's in there, but it's some other. There should be a follow-up to that paper,
Right.
which should do this.
Yes, because that paper is not monoidal, so but yeah, okay, I can imagine.
I think we don't really know why these classes are called eta, nu, and sigma. Once, so if you practice Kendo, you learn to count ishi, ni, san, e and s. So that's 1, 2, 3 in Japanese. So each that starts with E and an S as in eta, nu, and sigma. And I heard it was someone closer to the source who could confirm that this was not the original. So,
Yeah.
sorry?
Who called it eta original? I mean, these were the, like, what are
F0, F1, and F2. And then for a while, Sarah called what we call eta, he called it nu. So I think it's Toda who used eta, the current symbols for the first 20 cents or so. But as I said, someone said they had talked with Toda, and this was not the story. So push it any further. All right, thanks. That's not good yet.